Hello everyone. So we are going to start the part 4 from the topic rheology. So in this part 4 we are going to learn about the thixotropy, a essential phenomenon which is used in the pharmaceutical unit dosage form. So without wasting any time, let's start our presentation. So the thing is that thixotropy, the term. What do you mean by thixotropy? So let us start. So you see, as we have already discussed, whenever we apply a stress, right, a shear stress, a force F over a liquid solution or a liquid dosage form, right, if the liquid dosage form, if it is of Newtonian system, or if the liquid dosage form, they follow the Newtonian rule, generally what happens? After letting the liquid, after removing the force applied on the liquid, once we remove the force applied on the liquid will immediately come back to its original state. Suppose this is the graph. Here I am showing you the rate of shear G and the shearing force or shearing stress F. So this green color, right? Once we have applied the force, it will be directly proportional. It will move towards this way. Upon releasing the force, this will revert back. With this blue arrow, this will revert back to its original form. That is, they have a identical downward curve. This is known as the downward curve. But now thixotropy. In case of non-Newtonian, if we remove the stress or shearing stress force from a non-Newtonian system, what they actually do, in case of, suppose this green line, this is the force we have applied over a non-Newtonian system. Upon reaching this point, we have released the force. So the non-Newtonian system, what they used to do, upon releasing, they slowly revert back something close to its original form. It is close but not the same, right? Here it is same. Upon applying the force, it is going in the same direction, or you can say it is directly proportional. Upon releasing the force, it is directly proportional. But here, upon applying the force, this will show a curve like this. But once we have released the force, it will come back in a revert direction. But it is something close to the original, but not the original, right? The green line, it is the original. The blue line, it is the revert line, right? So they do not have the identical curve. So this phenomenon, it is known as the thixotropy. So by definition, you see, the thixotropy can be defined as a isothermal, means the process, it generally takes place in the same temperature and comparatively slow recovery. It is a slow recovery of the material upon standing, of a consistency lost through the shearing. So you can see the consistency. If we take the slope, here the slope A, it is, here the slope A, it is smaller than that of the slope B. Thus you can say the viscosity of A is greater as compared to the viscosity of B. So this is the thixotropy, means upon releasing the force on a non-Newtonian system, the non-Newtonian system will revert back to its original form, but the consistency may not remain same, as well as their curve, the downward curve, may not remain same as that of the previous one. Clear? So now the next thing, it is the negative thixotropy. What is that? Simple. Negative thixotropy, it is also known as the anti-thixotropy. It represents an increase. Earlier the viscosity has decreased, right? But here increase in the consistency in the downward curve. So this is the force we have applied, right? This green arrow, this is the force we have applied here. Upon reaching this point, we have released the force, we have released the shearing stress. So it will revert back. It will revert back via this curve, right? This blue curve, right? So you can see here what actually happens. The slope A, here this slope A, it is greater as compared to that of the slope B, and the viscosity of A, it is smaller as compared to that of the viscosity of B. It is just opposite to that of the thixotropy, means it is the negative thixotropy. I am trying to make you understand with this particular step. Suppose this is a system, right? Now here we have applied the force. Upon releasing the force, it has come to the rest, and finally it has reached this state. You see, once it will reach this state, the viscosity or the consistency of the particle will increase. Clear? So this is the negative thixotropy. Now the degree of hysteresis. So what do you mean by the degree of hysteresis? Simple. The difference between the upward and the downward curve. Just simply remember the difference between the upward curve. This is the upward curve, and this is the downward or revert back curve. The difference between the upward and the downward curve, it is known as, but the system should be thixotropic. So the difference in the upward and the downward curve in the thixotropic system, it is known as the degree of hysteresis. So as the product with high molecular weight will take longer to recover, their degree of hysteresis will be larger. The product, if there is a liquid product with particles of high molecular weight, this product will take longer time to settle down. So they thus have a high hysteresis as compared to a low molecular weight particle. If the system have a low molecular weight particle, it will somehow come easily back to, or it will somehow come close to the original form. Thus the degree of hysteresis will be low. Thus I repeat, the molecular weight, high molecular weight substance present in a system, in a liquid system, will have a high degree of hysteresis, whereas the low molecular weight particles will have a low degree of hysteresis. Now, when this mechanism thixotropy is useful in the pharmacy, see, in the field of pharmacy, thixotropy is very important. Shear thinning, it is very useful for suspension and cream. Whenever we press the tube, the cream, or generally the cream, it comes out, right? So this cream, it comes out as because the viscosity of the cream, it decreases. Similarly, in case of suspension, if we shake it, if we shake the bottle of the suspension, the van der Waals forces of attraction gets distorted, the particles get equally distributed, and thus it comes out in a uniform dose. So you see, increase in the viscosity at the rest, if the system it is allowed to be in the rest, the viscosity of the system, it increases, and when the viscosity of the system increases, definitely the stability of the system, it is also increased. Similarly, thinning with agitation. In case of suspension, if we shake the bottle containing a suspension, the particle get separated out. Earlier they may form, here we have shown, earlier they will form a globular structure, then they will form a triangle branch, and finally they will form a linear in case of polymeric solution, for example polysaccharide, right? So thinning with agitation, if we apply agitation in a bottle containing the polysaccharide at the rest, immediately what will happen? They will get separated from one another, right? And this helps in the easy administration of the dose. Clear? Thus, this thixotropy is useful as it is delay in the reversion to the original viscosity. Does it ensure the product administered before it get thickens up again? I repeat, thixotropy is useful as the delay in the reversion to its original viscosity. Suppose we have shaken the bottle, and the bottle, after shaking, the particle gets separated, right? If it immediately comes down, then we don't get a uniform dose upon pouring the content of the bottle in a teaspoon, right? But if the system have a high degree of thixotropy, what will happen? After the shaking the bottle, the suspension, the particles of the suspension, they will remain suspended over the dispersion medium, which ensure you to give a ideal and equal dose every time to the patient. Yeah. Now, one more concept is there. This concept is known as the intramuscular depot injection. I hope all of you have already taken intramuscular injection in the form of vaccines, right? Even we have taken the tetanus vaccine, right? So the vaccine they are given intramuscularly. In administration of the vaccine, actually, the concept of Thixotropy is used. You just see how it is used. See, high shear stress through the needle. So first, the sample it is withdrawn from the vial of the vaccine, right? Within the vial we have the vaccine. It is withdrawn via the needle into the syringe. So afterwards, the plunger of the syringe it is pushed. This pushing, this shear stress, it decreases the viscosity and helps the content of the syringe, that is the vaccine, to be easily move out from the needle, right? This thinning allows actually the easy administration, right? Now, at relatively rest in the muscle, suppose you have taken the content in the syringe, now you have pushed the content in the muscles, right? This is the muscles, this is the layer of the muscles, you have put it in the deep tissue within the muscles. So what will happen at the relative rest in the muscle, the viscous depot that we have pushed within the person, right? The viscous depot which can release the drug slowly over a long period of time, means upon pushing it within the muscles, the vaccine it will form a viscous depot. It will form a viscous depot from where slowly and slowly the drug will come out and it will act for a long time or long duration of time. So the suspension was not thixotropic. In such cases, it would be too thin in the muscle to form a depot. So the vaccine or the suspension, whatever it is administered in the muscle, they should have the certain viscosity or consistency so that they can form the depot. And if the suspension don't have such viscosity or consistency, it will not form the depot and it will not be helpful to the patient. Thus the intramuscular depot formation, it totally use the concept of thixotropy. Clear? So thank you everyone. Hope you have liked the video. If you like the video, just press the like icon. You can share this video and you can subscribe to my channel. Thank you once again.